How our thermal protection system risks managed during spacecraft reentry. Imagine flying through the atmosphere at thousands of miles per hour and facing temperatures hotter than boiling water. That's what reentry feels like for a spacecraft. Managing the risks involved is a complex process that combines science, engineering, and careful planning. When a spacecraft reenters a planet's atmosphere, it faces extreme heat caused by air compression and friction. Temperatures can soar past 3,000 degrees Fahrenheit, enough to melt most materials. To handle this, engineers design a special heat shield called a thermal protection system, or TPS. This shield is made of layers of materials that reflected, absorb, and dissipate heat. The most exposed parts, like the nose cone and leading edges, are built with materials that can withstand the highest temperatures. These materials include ablative substances that burn away gradually, carrying heat away from the spacecraft. They also use insulative tiles or blankets that resist heat transfer and high-temperature metals that absorb and re-radiate heat. All these materials undergo rigorous testing to ensure they can handle the intense conditions of reentry. Engineers use computer models to simulate the reentry process, predicting how the TPS will respond to different speeds and atmospheric conditions. These models are checked against experimental data to make sure they are accurate. This helps optimize the design, making the shield as light as possible while still offering maximum protection. During the mission, the spacecraft's reentry trajectory and speed are carefully controlled. Precise navigation ensures the spacecraft enters the atmosphere at the right angle and velocity. Too steep, and the heat load could be overwhelming. Too shallow, and the spacecraft might skip off the atmosphere. Small gaps between TPS components can cause turbulent airflow and localized heating. To prevent this, special gap fillers made of heat-resistant materials are used to seal these spaces. Regular inspections and maintenance are essential to keep these fillers in place. Researchers are also working on advanced materials that can heal themselves if damaged during orbit, helping maintain the integrity of the shield. For astronauts, training includes understanding how the TPS works and what to do if damage occurs. Mission planners incorporate detailed risk assessments into their reentry profiles, ensuring safety margins are in place. All these measures work together to manage the risks of thermal protection during reentry, making sure the spacecraft and crew arrive safely back on Earth.